Hi everybody, welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book, and I've been talking about group theory for the last month or so, I think, and I'm talking about a lot of different kinds of groups. Right now I'm talking about 3D symmetry groups, in particular rotation groups and symmetry groups pertaining to platonic solids, and there's a total of 6 of them altogether. There's 3 rotation groups and 3 symmetry groups, because there's tetrahedral, which corresponds to a regular tetrahedron. I've got a model right here, by the way. I'm going to demonstrate for this model. I don't know if you can see the numbers on here. I can't. But so there's a tetrahedron, and then there's also the cube and the octahedron. Both of those have the same groups, both rotation groups and symmetry groups. Those are called the octahedral rotation group and symmetry group. And then you've got the dodecahedron and the icosahedron, and both of them have rotation groups and symmetry groups as well. So anyway, let's begin. So the tetrahedral rotation group. So now here's a picture of a tetrahedron, and I've actually got my own model right here. I don't know if you can see the numbers I wrote out. I should have written letters anyway. Maybe I can fix this. I might as well do this one. Nah, I don't think I can fix it because it's going to take a long time. But so I'm going to orient this tetrahedron the same way it's shown in this picture. I've used numbers instead of letters. That's another problem. I did this kind of at the last minute, but I've got so the vertex A, if you notice on this picture, is on top, and then you've got B, C, and D on the bottom. I labeled those 2, 3, and 4, and I guess according to this picture, B and D, that would be 2 and 4. So this kind of looks like what's shown on the slide. Anyway, that's our tetrahedron. And now we want to apply rotations to the tetrahedron. So what kind of rotations can we do? Well, there's always the identity element, which does nothing. And remember, that's what we call E. That's always an element of every group. But then I guess the next type of rotations are the rotations about the centers of each face. So imagine you've got these 4 axes, because there's 4 faces to the tetrahedron. You got 4 axes, each of which goes through the center of a face and the opposite vertex. So you can see on this picture, the red axis shown in this picture is the rotation axis about that goes through the vertex A and through the face, which I think I call A prime. Yeah. So I labeled the faces with primes. There's a face that has the same letter on this picture opposite the vertex. So we've got the vertex A and the face A prime, and we can rotate about that axis. So for instance, we can do that. That's a 120-degree counterclockwise rotation. We can do it again. We can do it a total of 3 times, and when we do it 3 times, we get back where we started. So this is an element of order 3. We could give it a name if we want. I don't think I want to do it right now. But so that's another element. Actually, we've got 2 non-trivial elements if we do that, because we have a clockwise rotation, 120-degree clockwise rotation, also a 120-degree counterclockwise rotation. But we don't have to do it just about the vertical axis. There's 3 other axes as well. There's the axes that goes through the vertex B and the opposite face B prime. On my tetrahedron, which you probably can't see the numbers, that will correspond to the vertex label 2 and the opposite face label 2. I didn't prime these. I'm going to have to make better models next time. Sorry about this. At least I have models, which I think is better than not having them. But anyway, so if we can do the same thing about that axis, go 120 degrees counterclockwise, do it twice, and get back where we started. So that's another 2 elements, the 120-degree clockwise rotation, 120-degree counterclockwise rotation. We can do that about also the vertices marked C, the vertex marked C, and the opposite face marked C prime on my tetrahedron. That would be the face 3 and the opposite vertex 3. So we can rotate about that one once, twice, and get back where we started. So again, another 2 non-trivial rotations about that axis. And finally, we've got the green axis on this picture, the axis that goes through the vertex I've labeled B in my book, and face B prime. That would be 4 and 4 prime. Here's the face 4, and the opposite vertex is 4 also. So we can do that and that. I'm going to get back where we started. So that's a total of 8. That's a total of 8 non-trivial rotations. That's 8 more elements to this group. So far we've identified 9 elements of this group. The identity and 8 threefold rotations, 120-degree rotations, either clockwise or counterclockwise, about these 4 axes I just told you about. But there's actually 3 more rotations. So we don't have to rotate about one of those axes. There's 3 more axes we can rotate about, namely axes that pass through the centers of opposite edges. I think those are a little harder to visualize. I show them in this picture, though. So notice that we've got the midpoint of AB. That would be 1, 2 on my figure. That would be this point right here that I'm pointing to. I don't know if you can see that, but this is the 1, 2 edge, and the midpoint is where I'm pointing my left index finger. So we can take that point, and we can also take the opposite point. So for every edge, there's another edge that's skewed to it. There's exactly 2 edges that don't meet at a vertex. We've got 3 pairs of edges like that. We've got the pair of edges, the pair of midpoints. So we've got the midpoint of AB, and then opposite that we got the midpoint of CD. Notice that the edges AB and CD are what are called skew. That means that if we continued them infinitely far, they would never intersect, but they're not parallel. Those are known as skew lines. In 3 dimensions, you can have that happen. You can have lines that don't intersect and aren't parallel. Those are known as skew lines. So we've got the vertex passing through the midpoints of these 2 skew line segments, and that's the thing I marked in red. And we can do a 180-degree rotation about that axis. It's a little hard to do with this model, but in order to restore the tetrahedron back to what it looked like to begin with, we have to actually rotate 180 degrees. I think it's kind of easy to see that because you have to rotate the edge so that it still looks the same after you rotate it. And I think you know that you can rotate a line segment 180 degrees about its center and it still looks the same. And if you take this axis, it happens that both of these edges get rotated 180 degrees in such a way that they look the same afterwards. But the whole tetrahedron didn't get back to its original orientation. The vertices get switched around. It turns out that A and B get swapped or transposed, if you like, and C and D also get swapped, transposed. And then there's 2 other axes like that. I'm not going to continue demonstrating because it's a little bit of a pain, but I think you can see. I mean, on this picture, I show the green axis. That's the axis that passes through the midpoints of 2 and 3 of B and C, and also A and D, which I've marked as 2 and 3 and 1 and 4 in this picture. I might as well do it. So here's 2 other edges. Another pair of skew edges. We can rotate 180 degrees about that pair as well. And if we do it twice, we get back where we started. And finally, we've got the midpoints of AD and BC. In my model, those are 1, 4, and 2, 3. So we can rotate about that axis 180 degrees. And then we can do it one more time. So those are... that gives us 3 additional non-trivial rotations. Remember, when we do it once, we get back something we didn't start with. But when we do it twice, we get back what we started with. So doing it twice gives the identity. These are elements of order 2. The previous rotations I showed you are elements of order 3. So we've got 8 elements of order 3, namely the threefold rotations about each of these 4 axes, the ones passing through the vertices and the opposite faces. And then we've got an additional 3 elements of order 2, namely the 180-degree rotations about axes passing through the midpoints of opposite edges or skew edges, if you like. So that gives us a total of 12, because remember we have the identity. So the identity was one element, and then we had 8 threefold rotations, that makes 9, and then we have 3 twofold rotations, that makes 12. That's the group. And since it's a group, we can multiply elements. We can do multiple rotations. We can follow up one rotation with another rotation. That'll give you a third rotation. And I'm not going to bother showing you the multiplication table for this group. It turns out this group is isomorphic to A4, the alternating group on 4 letters. And I talk a little bit about this in the book, actually. Maybe I'll just tell you myself. So let's just think about what's going on here. How can we see that this group I just described to you is isomorphic to A4, the alternating group on 4 letters? Well, it's actually not that hard, because we've labeled all the vertices. I mean, forget about my model now. I'm not going to bother with a model. But just look at this picture. So we got our 4 vertices of our tetrahedron, which I labeled as A, B, C, and D. And we've got these, the identity doesn't do anything, so we don't really worry about what that one does. If you like, you can write it as, A in parentheses, and B in parentheses, and C in parentheses, and D in parentheses. I think I actually do that. Or you could just write it as E, if you like. But then we've got the 3 threefold rotations. Notice that each of the threefold rotations leaves one of the vertices alone. For instance, the vertical axis, the red axis. Notice the vertex A is on top. A stays put. A is a fixed point. But B gets sent to, if we're rotating counterclockwise, B, maybe we should go clockwise. If we're going clockwise, B goes to C, C goes to D, and D goes to B. So that would be in cyclic notation, that would be the rotation BCD in parentheses. I think I do show that on the last slide. So that's one of our 120 degree rotations. Yeah, A, B, C in parentheses, and then D in parentheses. And then there's another, there's actually 8 of these altogether. We can do the inverse of that. That would be ACB. It's easier to forget about the fixed point. So we have ABC, that's one rotation. That's the, let's just go back to our picture here. I guess ABC is the, it's not the one I showed you. It's the front face, if you like. It's the one. I mean, maybe I should show you the picture. So here's my tetrahedron. I'm calling them 1, 2, 3 here. I don't know if you can see this, but 4 is in the back. I labeled the face 4. The opposite vertex is 4. So we can rotate this 120 degrees clockwise, and if we do that, we get 1 goes to 2, 2 goes to 3, 3 goes to 1, but 4 stays fixed. We can do it counterclockwise, so we can that would make 1 go to 3, 3 go to 2, and 2 go to 1. But again, 4 stays fixed. And I don't think I want to do the other rotations. I think you get the idea. So each of these threefold rotations corresponds to a 3 cycle. And there's a total of 8 3 cycles in A4. 1, 2, 3, 1, 3, 2, 1, 2, 4, 1, 4, 2, 1, 3, 4, 1, 4, 3, 2, 3, 4, and 2, 4, 3. I just named them all. And I think you can see how they correspond to this picture. So, if you think about it, when you're rotating the tetrahedron, what are you doing the vertices? You're just permuting the vertices, right? And it turns out that every rotation corresponds to an even permutation of the vertices. In order to get odd permutations of the vertices, you have to reflect. And I'll do that tomorrow. Tomorrow I'm going to talk about the full symmetry group of the tetrahedron, which turns out to be isomorphic to S4, the full symmetry group of a set of cardinality 4, in this case the set of vertices A, B, C, D. So maybe the best way to think about these groups I'm talking about is permutation groups. So the group I'm talking today is just A4. It's the set of all even permutations of A, B, C, and D of the vertices. So I just described 8 of those. Actually, I described 9 because I described the identity. And then the last 3, I guess that's this picture. Yeah, these are the 8 threefold rotations. And then the 3 twofold rotations, that's just the product of 2 transpositions. So, for instance, if you rotate 180 degrees about the red axis, that would transpose A and B, but it would also transpose C and D. So in cyclic notation, we could write that as AB in parentheses times CD in parentheses. So that's for the red axis. For the green axis, is it the green axis or the blue axis? A little hard to see, but I think for the green axis, that's AC and BD. So that would fix that would flip A and C, and also flip B and D. That would be AC, the transposition AC times the transposition BD. And then the last one, the blue axis, would be AD, the transposition AD times the transposition BC. That's what these 180-degree rotations do to the vertices of the tetrahedron. They just corresponded product of two transpositions, two disjoint transpositions. So those are all 12 elements of the rotation group of the tetrahedral rotation group, and I think I just showed you that this group is isomorphic to A4 by identifying each element of the group with what it does to the vertices of the tetrahedron. So I think that completes my video for today on the tetrahedral rotation group. I'll make better cardboard models of these. There's 5 platonic solids all together, and I'll draw them more heavy so you can see them more clearly next time. I'll also use letters, because I think I do use letters on all the examples I give in my book. So anyway, that completes my video for today. Thank you for watching. Long live math, and I'll see you guys next. Bye.